Alright, hey guys, what's going on? So today we are going to be talking about general relativity from the ground up. We're going to talk more broadly in this video. So we finished talking about the special relativity stuff that I wanted to go over. And we're going to go over, again, really broad topics, and we're going to dive deep into them. And where the intent here is to go beyond other courses that you'll find on YouTube in general relativity so that we can get a more in-depth understanding here. So without further ado, make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support the channel. Now let's get straight to the topic. So today we are talking about more broadly general relativity. What is it? We're going to take a look at some of the key mathematical objects that we're going to want to take into account when we're studying general relativity. And we also want to take into account the physics, right? So in my playlist on tensor calculus, that was a mathematical playlist. Okay, this is going to be a physics playlist. So we're going to brush over the math. We're not really going to brush over the math. We're going to cover the mathematics, but we're quickly going to dive into the physics because this is, again, physics, not a mathematics playlist on the channel. So broadly speaking, the key mathematical objects that we are going to want to take into account or to keep in the forefront of our minds are going to be everything listed right here. So we have manifolds. We're going to talk a little bit about manifolds. We're not going to go too much in depth on them because there's a whole rich area of study on manifolds. We're just going to really briefly cover what exactly they are, how we can think of them in terms of physics. Then we're going to dive straight into the metric tensor, right? So the metric tensor is the most important thing that we are going to want to cover in this so that going forward things will be a lot easier to understand. Then the connection, right? So the connection, this is not a tensor. However, this connection is going to be pivotal in helping us understand and compare metrics at different points in spacetime, all right? Then we got the covariant derivative. The covariant derivative, again, super important. It's sort of the bedrock of all the other tensors that we're going to be talking about. Covariant derivative. The covariant derivative helps us, again, take derivatives of the metric on some manifold, okay? So this is what it means to take this, or this covariant derivative is going to give us the concept of a derivative on some curved space. Then we have the curvature tensor, right? So this is something that everyone covers in a GR course, in a tensor calculus course perhaps also. The curvature tensor is sort of the big daddy of these tensors. And then from the curvature tensor, we'll be able to understand the Ricci tensor, the Ricci scalar, and then taking all of these guys into account, we'll be able to understand the Weyl tensor, okay? Weyl tensor is something that more advanced, a topic that's more advanced. And then we're going to go to the Einstein tensor, right? So these are the main guys that we're going to talk about in this playlist. And I want to go through them pretty quick so that we can get to the physics, right? So the physics is going to be talking about geodesics, okay? We're going to start off understanding what a geodesic is. Broadly, we're going to derive the geodesic equation, okay? And then from there, we're going to go straight into understanding and deriving each and every one of these guys here, right? So through Einstein's coupled differential equation, right? So that's, I have that listed on the next page here. I'll come back to that page really quick, but this is the Einstein field equations, okay? And what it is, it's a series of coupled differential equations, and you can actually plug in those differential equations on a computer and figure out exactly what the paths or the trajectories of the geodesics are that they describe. So everything's going to hinge on our choice of the metric, okay? And these metrics are solutions to the series of coupled differential equations, okay? Now the metric is going to be different for each and every one of these guys here, okay? These are all metrics that describe different types of black holes, okay? So for a uncharged, non-rotating black hole, we have a Schwarzschild metric. For uncharged rotating black hole, we're going to derive the Kerr metric. For a charged non-rotating black hole, we're going to derive the Reisner-Nordstrom metric. And from a charged rotating black hole, we're going to get the Kerr-Newman metric. This guy's probably the most complex one, right? Because we have to take into account we have to take into account charged, and we have to take into account rotating, the rotation of black holes. Okay, the most simple one is the Schwarzschild metric. This is the one that almost everyone goes over when studying GR. And we're going to beat this one to death a lot. This one also, I hope we're going to beat this one to death also. It's going to be more complex and a little bit harder to understand probably. And then we get the Einstein-Hilbert action. So we don't get the action from these guys. What's going to happen here is that we're going to talk about all of these in separate videos. We're going to derive them. We're going to look at all the details that go into deriving them, what they mean, their implications. We're going to try to look at what their solutions look like. If given that we have the capacity to look at their solutions, and then we are going to go from there, and we're going to start talking about the Einstein-Hilbert action, right? So this is when we talk about actions, right? This is sort of bringing the language of quantum field theory into play here, or even just classical field theory. The idea here is that differential equations, right? So this here is a differential equation, and this differential equation, well, what gives rise to differential equations? Lagrangians, okay? So once we're done talking about the important metrics that describe, or the important, more common metrics that describe black holes, then we're going to get into taking a look at this guy here and asking ourselves, what's the Lagrangian that gives us this? Okay, and that we're going to start talking about the Weyl tensor within that context as well, because there's a lot of really interesting mathematical tricks that we can do to understand how the Weyl tensor plays a role in the Lagrangian for the Einstein-Hilbert action. Okay, so let's start here. We're actually going to start by talking about a manifold and briefly talking about a metric. Okay, so physically, what does it mean to have a metric on a manifold? So the idea here is, again, suppose you're standing on this manifold, but perhaps you're somewhere in the space-time. The manifold is four-dimensional, right? Here I'm just depicting it as 2 dimensions because I can't draw 4 dimensions. But we're sitting right here, say, and we have components t, x, y, and z right here. Okay, so it's some point in time, and then I can describe the 3 spatial vectors that describe my location as well. So at this point in space, we're holding a clock and a ruler, right? I should say ruler here. We are holding a clock and a ruler. So suppose I'm here in space at some moment in time. I'm holding a clock and I'm holding a ruler. This is all I really need to measure all the physical quantities in the world, right? So here I am with my clock and my ruler, and the question I want to ask here is, okay, as time proceeds, at some later point in time, and I could say I can walk to a different point on this manifold. I'm still holding my clock and my ruler. But given that it's curved, at some later point in space and time, my units might change, okay? So suppose, again, we're taking into account special relativity, we're taking into account the curvature of space and time. We know that through length contraction, time dilation, if I'm moving really fast and I'm on a curved surface, the idea here is that the units are going to change, right? So length contraction, say the ruler contracts, okay? time dilation. Say the clock starts ticking at a slower speed. Okay, so I'm moving on this manifold, and as I'm moving on the manifold, the ruler might stretch. It might undergo time dilation, or it might undergo length contraction. The clock I'm holding might undergo time dilation. Okay. The idea here again is that everything's dynamic. I'm holding a ruler and I'm holding a clock. Those are the only two things I'm holding as I'm traversing this manifold. Okay? So we want a tool, we want an object, some sort of mathematical object that puts all this information in one overarching thing, right? So all the information regarding how the clock ticks and how the ruler stretches and squeezes as we're moving along this manifold. And the metric tensor is going to account for this change. Okay, so suppose we are in the case of the black holes, this is going to be quite dramatic of a change, especially when you're getting closer to a black hole, because you start moving faster. Things move closer to the speed of light when you get closer to a black hole. And the idea here again is if I'm standing here holding my ruler and my clock, and I get close to a black hole, then I'm going to undergo length contraction and time dilation. So here's my ruler and my clock, and these guys are good since because we're going fast, because we're getting closer to the speed of light as we near this black hole. My ruler is going to undergo length contraction and my clock is going to undergo time dilation, and there's a hyperbolic relationship between these two guys here. Okay, so this is why special relativity always needs to be in the forefront of our mind also, right? Because when we're moving fast and when we're talking about black holes, this manifold is going to shape how we understand special relativity within this context as well. Okay, so again, we're holding a clock, we're holding a ruler, and we're continue to hold this clock and ruler as we get closer to this black hole. No one in their right mind, right, would get close to a black hole. But again, this is all theoretical. We know for a fact now that things undergo time contraction and length contraction and time dilation. And so this sort of naturally begs the question, what objects do we need, or what object do we need to encapsulate all the information here and all the information here, and how can we compare the information here to the information here? Okay? Well, let's look at this geometrically. And let's ask the question, how exactly is length measured? Okay? Well, suppose we have a distance here that we want to measure, ds. Well, we can construct ds into a coordinate system where we have x and y, and our ds is, by Pythagorean theorem, is x squared plus y squared. Okay, we can rename these guys to x1 and x2, and then keep them squared, and this is our length element. Okay, and then this is more of a generalization, right? This is x1 times x1, where mu is 1 and nu is 1. And then this is the metric tensor. This is going to tell us if the metric tensor is the metric tensor here can be 1 or 0 in the case of this right here. And so we have so this generalization gives us this back. Okay, now this can be something else, right? We can have mixed components here, and we'll take a look at all this, but the idea here again is we have a unit length, or a length, some sort of length. It's a number, okay? And this is how we compute it with the metric tensor, okay? So we feed the metric tensor in two vectors, and we get some number that represents a length, okay? And that's something to keep in mind as well. We want to feed this guy some two vectors, okay? Feeding it two vectors, and we get a number, right? So here's our number. And so what we have now is, well, I can construct my triangle here, but I can also construct my triangle here, okay? And so this G mu nu tells us how we can measure, how exactly we measure the length of the hypotenuse of that triangle at different points in space-time on this, and the manifold represents our space-time. So therefore the metric changes as a function of the distance from the black hole. Okay, so suppose, well, don't suppose, right? So we have, here's our black hole, here's the center of our black hole. Here's our radius, okay, and we're this far away from this point here, point P. And then say at this point here, we're this far away, our prime. Okay, so as we get close to a black hole, our notion of length changes. Again, that comes from length contraction and dilation. So we always want to keep special relativity at the forefront of our mind here as we're doing this. So if we know the metric, then we should be able to plug it into this equation right here to get some unit length. Okay, here's our two vectors, and this thing is a number. So this metric tensor is important in helping us understand or try to get exactly what this number is. And that number, again, represents some sort of unit distance, okay? When we're playing with four vectors, right, so here, just quickly for a second, here we're playing with just two dimensions. When we start talking about general relativity, though, we want to start talking about four dimensions, right? Time and the three spatial dimensions. I just use this here just as a very simple, just as a very simple means of understanding what length is. Right? Length in three dimensions is going to be, we have a Cartesian coordinate system, and then we have some vector, and that vector is going to have some x components and some y components, right? So x, y, z. Okay, so we have components there, and then we have the temporal component as well. And that's why we're talking about four vectors. That's why we're going to be talking about four vectors in this playlist. And so, okay, so this is all quite fun and good. The metric tensor is going to be at the bedrock of everything, but we can also think up of other objects that do similar things. Right here, we're feeding this thing two vectors, and we're getting a number. But we could say feed something three vectors and give it and have it produce another vector, or we can feed something two vectors and have it produce two vectors or something like that. And that's where the idea of tensors are going to come into play. So this is sort of going to be a new way of looking at tensors. All the things you've seen in the past on YouTube in classes, say, they all give you some way on how to think of tensors. A lot of them are formal. Formality usually comes with confusion, however. What I want to say simply is that a tensor, if you see, say, a tensor that looks like this, a very simple and easy way to think about this is each of these are going to sum over three separate vectors, okay? So your input, say you input three vectors here. Depending on how many up components here we have, and we'll talk about what these are covariant components to a tensor. But for right now, think of this thing as, okay, you have three down variables, or three subscripts. That means we're going to feed in three vectors, okay? And then the the superscript here is going to, it means that the output is going to be a vector. Okay. So we input 3 vectors, the output is 1 vector. Okay, this is a rank 1-3 tensor. Okay, 1-3 tensor. Similarly, we can say input 4 vectors and output 2 vectors. So we can construct these tensors. They're really machines or functions, if you will. You input some amount of vectors and you output some different amount of vectors, or the same amount of vectors. Similarly, this here is a rank 2-3 tensor, right? So actually this would be a 2-4 tensor, right? This would be a 2-4 tensor. Okay, and then right here, so this is kind of similar to the metric tensor because it's got 2 subscripts. You input 2 vectors just like we did right here, and the output is a single scalar, right? There's no superscript up here. So, and this is a rank 0-2 tensor, so 0-2. Okay. So that's the way I want to think about this, okay? Because when we're thinking physics, right, there's going to be these things called covectors, right? But that's somewhat of an abstraction, okay? There's some physical relevance to a covector, right? But we really want to talk, if we're really talking physics, we're talking about the real world. We're talking about objects that represent the real world, and vectors are going to be the name of the game here, okay? So we want to think of this in terms of vectors. And covectors, those are going to be something else that we're going to get into in the next video. But to sort of tie things off again, so some of the most common rank 0-2 tensors that we're going to come across are going to be these guys, and these are going to be the most important tensors that I argue are going to be relevant for general relativity. So the electromagnetic field tensor, F mu nu, the stress energy momentum tensor, T mu nu, and we're going to find a relationship between these two guys here, okay? Because when it comes time to start talking about solutions to the Einstein field equations, this guy here, when we start talking about the Reisner-Nordstrom metric and the Kerr-Newman metric, the idea here is that they're charged, right? So these black holes are charged, and the only way we can get charge into the stress energy momentum tensor is if we find a relationship between these two guys, because this is where we're going to talk. This is where charge is introduced in the context of magnetism. And then these 3 guys here, right? So the metric tensor, the Ricci tensor, and the Einstein tensor. And we're going to talk about these guys as well. So here's the Einstein field equations, right? So on one side of the equation we have geometry. Okay, we're talking about lengths here. This guy gave us some length. This guy's constructed from this guy. So this here is geometry, mathematics, straight up math and geometry, okay? And then this here's the physics, right? So T mu nu, we're going to be talking a lot about this T mu nu guy, and how we can think of it both in terms of electromagnetism and without electromagnetism. And because this is a differential equation, then we'll be able to talk about the Lagrangian formalism for this as well. So last but not least, so this is just a recap of what I've talked about in this video so far. Geodesics, differential equations, finding solutions to the differential equations, Einstein-Hilbert action. We also want to add Einstein-Maxwell, tensor, right? So T mu nu, there's going to be a relationship between T mu nu and F mu nu. That's what we want to talk about that as well, so that we could talk about the Reisner-Nordstrom metric and the Kerr-Newman metric. And then we're going to get into the Lagrangian formalism for GR. And this is going to spit us into a whole new area of quantum gravity. Because the idea here is once you have a Lagrangian, then you can get a Hamiltonian. Once you get a Hamiltonian, then we're sort of in the language of talking about quantum physics now. Okay? The idea here is that we're going to foliate space and time. We're going to take our metric tensor, we're going to separate the time component from the metric tensor with the spatial components, and we're going to see how the metric tensor evolves in time, okay? And that's going to give us the ADM formalism. And then I also want to talk about the ADS-CFT correspondence. This is going to require us to talk about some conformal field theory, though. And then this is all going to accumulate in quantum gravity, which may be part of this playlist, may be a separate playlist. But without further ado, I hope you enjoyed this. This was a big, brief overview of what's to come, and I want to get to this quick, right? I want to at least get to this pretty quick, okay? And then we're gonna, because I want to spend a lot of time on these guys. These are super, super interesting. ADM formalisms and the ADS-CFT correspondence. So if you like this kind of content, make sure to hit that like and subscribe button, and you can go onto my Patreon page to support the channel as well. And I'll see you guys in the next one. Bye.